So in this lesson, we're going to be taking a look at the new unit, looking at lines and planes with vectors. And the first section covers equations of lines in 2 space and 3 space. So just to take you back to grade 9 days, just to relate some of the concepts you looked at previously to what you're going to be taking a look at now. So in grade 9, you should be familiar with that equation, y equals mx plus b. And this is the standard form version you should also be pretty familiar with. And just a little funny little joke here. So today we're going to take a look at the vector side of the equation, not the dark side, but lightsaber does kind of remind you of a bit of a vector, doesn't it? Anyway, for those of you that are Star Wars fans, so let's take a look at the different parts of the equation that you're taking a look at here. So in this format, in some regards, it's best to rewrite it, because oftentimes you're taught to graph starting with the y-intercept and then using the slope to graph. So if you take a look at that as a rearrangement of the equation of a line from grade 9, m is your slope. Slope tells you what direction the line is going in. So there's your rise and your run, or your run and your rise, I should say, to determine the slope. So what can happen with vectors is you can draw a vector connecting 2 points on the line that represent the direction the line has to follow. And that's what we're going to be examining a little bit, and then some of the algebra that's with it. Excuse me. And some of the different algebraic terms. So in grade 9, you would have seen these different variables, it might have been called, but they're actually called parameters. Parameters is a fancy way of just saying values that can change. So here is the component form, just to talk about the looking of it, so in vector equation. So just to take a look and compare. So the generic format for component form is xy. This first part represents a specific point on the line in 2-dimensional space. Well, so does the y-intercept in the grade 9 version. Then there is a parameter followed by a vector that represents its direction. So let's take a look at the equation. So you have a slope that represents the direction, and then a variable for the dynamic changing aspects. So from a visual point of view, this here is your position vector to any point on the line. It doesn't have to be the y-intercept. This would represent the direction to follow for your line. Now remember, the direction can be in an upward direction, but for vectors, it could also be in a downward direction. It's a little unique. And what this is allowing you to do is take scalar multiples of this direction vector. So whether you're taking the full direction vector, you're going to take 2 of them, or you're going to take half of them. But using that direction vector, you can access any point on that line using that direction vector. So even if the k value is negative, you can locate all the points on the line. And that's what an equation of a line is all about. It's a way of finding all the different points on the line in an infinite manner. So if you take a look at why this is referred to as R, think of resultant. So you take this vector, add the direction vector, and you get your resultant, much like similar concepts you learned before. Typically, the parameter that is used is t, that you'll notice often. Doesn't have to be, but there's different forms for these equations. So you could have r vector and then r with a little o there, representing what's called a position vector to any point. Then there's a parameter, and then m with a little vector is the direction vector of the line, representing the direction of the line, much like slope. Okay, so there's a lot of just similarities in getting through some of these things. Parametric equations are basically ways of just writing independent components. So your line can be broken up into an x component and a y component. The x component follows all the x portions. So x naught plus tmx, and then the y follows the y portions. Right, so just breaking it into different parts. So that would be referred to as parametric equations. Symmetric equations come from taking both of these equations and solving for t. And since when you do that, if you solve for t, these must be equivalent, these expressions here. And that's what's known as a symmetric equation. So much like in grade 9, you have slope y intercept form, you have standard form, you have intercept form. There's different forms for the equations, and they just have different names. All right, but the letters represent exactly the same thing in all three of them. They just look kind of different. So to determine vector, parametric, and scalar Cartesian equation that passes through the lines, it's like a grade 9 question. So in grade 9, you would have plotted the 2 points and then found the slope of the line. But in this case, what we're looking at is not the slope, but we want the slope vector. So we can find the vector between A and B. So it could be either written as AB vector or BA vector, it doesn't really matter. So to get its direction, we're simply using vector AB. And then we need a position vector to any point on that line. So that would be either that one there or that one there. Doesn't really matter which one. That's the interesting with vector equations in component form, is that this point here could have been the 1, 2, but it could also be a 4, 7. So that's a little unique when it comes to vector equations in component form. So that's your vector equation. Your symmetric equations, your parametric equations again come from just taking the x components and writing it out in a certain way, and then taking the y components and writing those out in a separate way. And that's what we have here. So x equals 1 plus t3, or 3t, and then y equals 2 plus t5, or 5t. And then solving for t in each one of these gives us this. Now, this is a quick way of solving, so it's basically subtract 1 from both sides, divide by 3. Subtract 2 from both sides, divide by 5, and that's where these are coming from, and they must both be equal to t, so that's a quick way of getting the symmetric equations. Each one of these different styles have different advantages that you may see or may not see, depending on the type of questions you're dealing with. Now, to get the Cartesian equation that you saw in grade 9, well, if you look at the symmetric equation, it already has the basis for what you need. It has an x and y variable. So all you really need to do is just rewrite this equation here in a format that looks like that. So you can multiply both sides by 5, then multiply both sides by 3, and then algebraically manipulate to do, or to write it in this particular format. That's all we're doing here. Multiplying, or cross multiplication will also work, and then rewriting it in the form that's required for the Cartesian equation. Okay. Keep in mind the Cartesian equation could also have 2 different looks to it. So again, that could be a little bit unsettling when you have different answers, but that's why I'm just pointing that out here. Okay, so let's say you want to determine a position vector that's perpendicular to the line determined by part A. Now, normal vector is perpendicular to a line, and there could be multiple different normal vectors. So here's one normal vector, but it could be smaller, it could be longer, it could even be pointing in a different direction. Now, things that are perpendicular, that should remind you of using things like dot product. So if you have a direction vector for the line, which is your slope direction vector, if you wish to call it that, then all you really need to do then is do this sort of thing. So find the generic normal vector, or a normal vector. If the dot product with the direction vector should be 0 because they're going to be perpendicular. Remember that concept. Then you just algebraically manipulate that expression. So xy dot over 3, 5, and as the dot product tells us, it's 3 times 5 plus 5 times y. That gives us an equation. Now, what we're allowed to do is to choose any number, because again, there's multiple vectors that will be perpendicular. It doesn't really matter what the magnitude is, as long as the direction is okay. So you choose any value for x or y, substitute it, and then get your normal vector. All right, so randomly choose a y value, solve for x, and you get a normal vector. Okay, so there's multiple normal vectors that can be found, an infinite number as a matter of fact, because you can draw as many normal vectors as you'd like in any direction as long as it's perpendicular to that line. Okay, now if you take a look at the components of the normal vector, the coefficients of the scalar equations, well, let's just go back. So look here, we got a -5 and a 3. Let's go back here for a moment. A -5 and a 3. Well, nothing here jumps out, but what about here? Look at that. -5 and +3 coefficients for those things. That is not an accident. Okay, it's not coincidental. It's just a mathematical fact. All right, so just that'll help us out with some other questions. So to find coordinates of another point on the line using the parametric equations. Now to get parametric equations, remember this is a continuation of the previous example we first started with. So there's the parametric equations. You essentially just choose a t-value. Any t-value you want, because t is a parameter, it could be any number you'd like, it could be positive, it could be negative, whatever you'd like. And you'll solve for x and y, and another point would be 19 and 32. You can also get all sorts of things there. Infinite number, of course. All right, new example. So determine if the following lines are coincident. So remember, for coincident lines have to be parallel, so they have to have parallel quantity, and coincidental back in grade 9 they would have also have the same y-intercept. So let's take a look here. So for parallelism, what we're looking at is we want to focus on these direction vectors. So if these direction vectors are exactly the same or scalar multiples, then the lines are definitely parallel. Now, parallel doesn't mean coincident, it just means parallel. Coincident means they're exactly the same, so we'll have to do a little bit more. So if they're scalar multiples, then the lines are parallel, which means they could be coincidental. So one way of testing is taking a look at the direction vectors first to see if they're parallel, and checking to see if they have basically if the lines have the same slope. So in other words, are they scalar multiples of one another? Okay, so that's one way to do it. Sometimes it can be done visually. You can just say multiplying -3 by 2, -2 gives us +6, and then multiply the same value by 4, does that give you -8? And if you get a true statement, then you're good to say that they're parallel, or you can algebraically prove it like I'm showing you here. Okay, so since they are scalar multiples, so this one way to do it is to set up a ratio. So a ratio, or basically calculate the slopes using what you have here. So the y component divided by the x component. If you get the same slopes, then they're parallel, right? There are different techniques for proving that. And you'll see that in the textbook and in online situations as well. So you know that 3, 2 lies on the lines I was getting earlier, right here. So that is the point on the line, even though it's a position vector. It's, remember, this is a position vector to a point on the line. So 3, 2 has to be on the line. So if we're trying to determine if it's coincidental or not, we want to see if this point is also on this line. How do we do that? Well, we can set up a different system here of parametric equations. So again, we can rewrite the parametric equations, replacing the x's and the y's, and then solve for t. And if we get the same t value when we solve, then we know that the point 3, 2 is on this line as well. Okay, and through a little bit of solving, we wind up getting 2 different t values. So we can say that the lines are parallel, but they're not coincidental because one point is not also on the other line. Okay, a couple more things to get through. Find the scalar equation of a line that passes through this point and has a normal vector. So you want this. Now, there's different techniques to using this. And we saw earlier that the coefficients represent the values in the normal vector. We're going to do that in a moment. But here, to use the dot product, what you can do is you can try to get a little visual on this. So it has to pass through the point 2, 5. So roughly here. So 2 and then 5. So that would be P0. And the normal vector is 3, -5. So there's a normal vector drawn just for reference. You could draw it right from point P, which means you'd have to go 3 to the right and 5 down to get that normal vector, following what the normal vector tells us. But to get the equation of a line, we need to talk about something a little bit different. Now, to get the direction vector, we do know that the direction vector of the normal will produce at 0 with the dot product, so we can then go ahead and solve that. And if you notice, what we're also doing, though, to get the scalar equations, we're just picking a generic point P with variables x and y. So the direction vector that we're allowing to choose here is P subscript 0P, okay? And to get that to the component form, well, we don't know the point P, so we take the x component, subtract the 2 from the original, and we don't know the y value for that general point, so we subtract 5. So that's basically just setting up a vector between those 2 points, and we get it in component form. Dotted with 3, -5 should be 0. That'll give us an algebraic expression that has the variables x and y, and that's all we were really looking for, is to be able to do that. And there's a scalar equation. Okay. Alternatively, using the scalar form, so again, we already know that those components of the normal vector are going to be the same as the a and the b. So very simply then, if we have the a value and the b value, and we know it should result in c, and we also know it passes through point 2 and 5. So we can also replace the x and the y, much like you would have done in grade 9 finding equations of lines. So this is coming from the normal vector, the 3 and the -5. The 2 and the 5 are coming from the x and the y. And then we simply need to solve for c, and we'll get that result. Same equation as we did earlier. Okay, so this is the first part of the introduction to equations of lines in 2 dimensions, and we'll look at 3 dimensions momentarily.